Inside an industrial pipe, raw wastewater carries heavy mineral salts, dissolved chemical residues, and toxic waste, pushing thousands of gallons through a spiral plastic sheet under massive hydraulic pressure, forces clean water molecules through tiny pores while blocking dissolved contaminants. This physical separation process, known as reverse osmosis, serves as the primary physical line of defense in modern water treatment systems across the manufacturing world. Massive electric pumps roar continuously as they generate high pressure, driving dirty fluid against thin polymer layers wrapped tightly around central collection tubes. If the internal pressure drops even slightly, contaminated fluid leaks back into the clean stream. If the pressure rises too high, the delicate plastic sheets tear apart instantly, causing thousands of dollars in physical equipment damage and bringing factory operations to a sudden standstill. For decades, heavy manufacturing relied on a wasteful linear model. Industrial facilities continuously pulled millions of gallons of fresh groundwater from nearby rivers, used it once to cool scorching steel or wash chemical tanks, and dumped the polluted wastewater directly back into natural waterways. This relentless drain dried up regional aquifers, contaminated clean rivers, and created severe environmental conflicts with surrounding local communities. Transforming that destructive linear flow into modern closed-loop manufacturing requires stripping every pollutant out of process liquid so it can be reused immediately. Advanced reverse osmosis membranes remove microscopic chemicals and heavy metals, converting foul industrial wastewater back into ultra-pure liquid. This continuous recycling process keeps millions of gallons moving inside factory walls indefinitely, eliminating the constant need for fresh environmental water withdrawal. Yet these microscopic filters face a constant physical operational hazard known as membrane fouling. Over time, heavy mineral scale builds up on the fine filter mesh, blocking fluid movement and straining high-pressure pumps. Biological slime can also spread across the plastic sheets within hours, raising internal pressure and destroying the delicate physical barrier if plant operators fail to flush the system with special chemical washes. Preventing catastrophic filter damage requires continuous vigilance far beyond human physical capabilities. Digital control networks, known as SCADA systems, continuously track thousands of live data points across the complex piping matrix. SCADA networks measure pressure differences, liquid flow rates, and chemical balances every fraction of a second, spotting invisible operational shifts deep inside sealed metal pipes long before physical damage occurs on the factory floor. When automated sensors register a sudden pressure spike across a membrane bank, the control software acts instantly without waiting for human intervention. Central digital signals trigger automated motor valves, instantly rerouting high-pressure fluid into secondary clean pipes. At the same time, computer-controlled feed pumps adjust chemical dosing levels to dissolve mineral scale before it can permanently ruin the expensive synthetic plastic filter elements. High-tech semiconductor fabrication facilities and massive automotive manufacturing plants rely heavily on these integrated loops to sustain daily production. Microchip manufacturing requires hyper-pure water stripped of every single foreign particle to rinse sensitive silicon wafers during production. Without continuous reverse osmosis purification and precise SCADA monitoring, a single contaminated drop of water could ruin millions of dollars in microchip inventory during fabrication. Long before contaminated wastewater reaches the delicate filter sheets, preliminary treatment stages remove heavy physical debris. Settling basins and coarse sand filters trap suspended gravel, heavy oils, and floating sludge from the incoming fluid stream. This essential pre-treatment prevents sharp particles from tearing through micro-thin membranes, protecting the delicate high-pressure filtration zone downstream, where atomic-level chemical separation takes place. Deep within the processing facility, programmable logic controllers receive direct electric signals from submerged sensors. These compact computing units convert fluid pressure, flow velocity, and chemical concentration readings into precise digital data packets. Local controllers transmit these measurements over industrial network cables directly to central SCADA servers, creating a complete real-time digital map of every pipe, valve, and pump across the complex. Human operators no longer spend long shifts manually turning heavy iron valves or testing water samples with glass tubes. Instead, engineers sit inside quiet control rooms, monitoring digital display screens that render live flow paths and color-coded status alerts. This automated technology shifts human labor from dangerous physical toil to strategic supervision, allowing small teams to safely manage massive industrial water recycling networks without interruption. Inside the tightly wound membrane coils, physical separation happens at the ionic level. Water molecules are forced through dense synthetic polymer chains by high-pressure pumps, leaving behind dissolved salts and toxic organic pollutants. The concentrated waste stream, known as brine, is directed into a separate discharge line, ensuring the dirty particles never contaminate the purified stream, returning directly to the production line. Forcing liquid through micro-thin atomic filters requires massive electrical energy, creating heavy power demands for industrial plants. To solve this efficiency challenge, modern recycling facilities install energy recovery turbines that capture mechanical force from the outgoing high-pressure waste stream. These specialized devices feed hydraulic energy directly back into incoming fluid pumps, cutting overall electricity consumption across the recycling plant by nearly 60%. The positive impact of this technical balance extends far beyond factory walls into local communities. By recycling over 95% of their operational liquid, heavy industrial plants stop drawing fresh water from regional river basins. Towns surrounding these manufacturing hubs retain their local drinking supplies during severe regional droughts, proving that closed-loop production can protect public water security while maintaining full economic output. Modern SCADA software does far more than monitor current conditions. It uses advanced predictive algorithms to prevent unexpected equipment failure. By analyzing historical pressure curves and flow trends over many months, the software accurately predicts when filter membranes will clog. Maintenance crews can schedule filter cleaning during planned plant downtime, avoiding costly emergency shutdowns and keeping critical production lines running without expensive delays. Chemical control inside the continuous liquid loop remains a precise and ongoing operational challenge. If recycled water becomes slightly acidic, it corrodes metal supply pipes and damages heavy pump impellers. If it becomes too alkaline, mineral crusts build up quickly across the filtration sheets. Automated dosing pumps continuously inject balancing chemicals, holding liquid properties within tight parameters to safeguard critical manufacturing equipment. In modern industrial parks, water recycling loops now connect multiple independent manufacturing facilities together. Clean wastewater discharged from a light electronics assembly plant is piped directly to a neighboring power plant to cool high-temperature steam turbines. Integrated SCADA systems link these separate facilities, automatically managing multi-factory fluid transfers through networked control valves that dynamically balance regional industrial water supplies. In arid desert regions, large-scale industrial construction was once impossible due to the total lack of local freshwater supplies. Modern reverse osmosis technology, combined with digital SCADA systems, completely transform this geographical reality. Manufacturing plants now operate successfully in hot desert landscapes, continuously recycling their internal water supplies while losing only small fractions of liquid to natural atmospheric evaporation. To achieve complete closed-loop efficiency, industrial facilities install zero liquid discharge systems to eliminate remaining wastewater. Large thermal evaporators boil off concentrated brine streams, turning hazardous liquid waste into dry, solid mineral cakes. These solid residual salts are safely harvested for chemical recycling or secure disposal, ensuring that zero liquid pollution leaves the facility to damage surrounding natural groundwater ecosystems. Because digital control networks command vital physical infrastructure, securing SCADA systems against cyber threats is extremely critical. Dedicated industrial firewalls shield communication lines from external intrusion attempts that could alter chemical dosing parameters or override pressure safeguards. Encrypted networks and isolated physical controls ensure that critical water treatment hardware remains completely protected from malicious digital disruption and remote operational sabotage. Tightening environmental regulations and rising freshwater costs are forcing industrial companies worldwide to adopt closed-loop systems. Facilities that continue using outdated single-use water methods face escalating municipal fees and severe operational cutbacks during regional water shortages. Automated water recycling has shifted from an optional green initiative into a mandatory economic requirement for modern global manufacturing across every industrial sector. As artificial intelligence merges with industrial automation, water recycling systems are evolving into fully autonomous networks. Advanced synthetic membranes are growing stronger and more chemical resistant, while self-learning SCADA algorithms dynamically reconfigure fluid pathways around failing pumps. Through this seamless combination of advanced physical filtration and digital control, heavy industry is building a sustainable future where manufacturing thrives without exhausting Earth's precious freshwater resources.